So thanks very much, Susanna. A very good afternoon to you all. My name is Andrew Morris, and it's a pleasure for me to introduce to you the LEVITATE project. During this session this afternoon, I'm going to talk to you a little bit about what the project is doing so you can understand the aims and objectives of the project and what we're trying to achieve. And then I'm going to discuss some of the methods that we've selected within the project, together with a brief description of the results that we're already seeing in the project. And I have to say from the outset that we're generating so much data in the project that within the 15-minute presentation, obviously all I can do is really scratch the surface of what we've done. So hopefully if you want to follow on this particular session with more discussions, we'll be glad to talk further with you. First of all, LEVITATE stands for Societal Level Impacts of Connected and Automated Vehicles. And the attention all along has been within the project that we're going to build tools that will help the European cities, regions and national governments prepare for a future with increasing levels of automation in passenger cars, urban transport and urban logistics. The project funding is 6.4 million provided by the European Commission within Horizon 2020, and the project, which has been led by ourselves at Loughborough University, brings together 12 partners from 10 countries, including a number of research institutions, local authorities and global partners. It's a 3-year project and it started in December 2018. The partnership addresses the combination of technical, stakeholder and implementation challenges which are involved in conducting the necessary research to develop what we're claiming to be a policy support tool. The team, as you can see here, is assembled in order to combine all of the competencies and expertise in order to carry out technology evaluations through data analysis and simulation modelling to ensure that we, first of all, achieve our required results, and then we're able to disseminate the results and exploit the project results amongst those who want to use the policy support tool. And then ultimately we want to launch the policy support tool to be used by the stakeholders, including the local and national roads authorities and policymakers. So hopefully you can see here there's a good blend of research institutions, universities, software and simulation experts and road authorities involved in the project. There's good justification for the project. We believe overall there's high expectations and quite a lot of optimism about what connected and autonomous transport systems are going to deliver in terms of safety, mobility, environmental benefits, etc. But as I'm sure you realise, there's no standard means as yet to predict what's really likely to happen when all of the predicted benefits are likely to eventuate, or whether there might be issues with, for example, the introduction of automated transport systems that we've not yet realised or anticipated. And also, maybe a little bit less obviously, we need to consider whether the potential benefits that we might predict in one particular metric do not necessarily mean that there's a detrimental impact on another metric. So we need to consider all of the likely benefits and disbenefits collectively. And as you can imagine, doing this sort of analysis is quite challenging and complex, but it's no less important or necessary. So the overall aim of LEVITATE really can be described as building the tools that will help European cities and other cities for that matter, internationally, regions and national governments to prepare for what we think is a future with increasing levels of automation in passenger vehicles and other urban transport services and urban logistics. We're actively developing the impact assessment framework, which will be available to the policymakers so that they can manage the introduction of automated transport to maximum effect. And this will in turn allow that the technology can be harnessed in order to achieve what we think are the current societal objectives. To achieve its objectives, LEVITATE has established a number of impact assessment methodologies, so it's just worth touching on these for a second so you can understand the sorts of things that we've done within the project to get the results that we're already seeing. We're considering how these can be applied across a range of possible future scenarios once automated vehicles become a reality based on stakeholder inputs, quantification of impact dimensions and indicators, and development of micro-simulation models. For example, we might want to consider how driverless cars will impact on parking provisions within inner city areas. And we might want to determine what the likely traffic flow into city centres might be if we decided to provide dedicated lanes for driverless cars. So we started out in the project by considering a wide range of use cases, and what we've done now is we're at the point of where we're trying to embed the results from these use case analysis into the policy support tool. And as I said before, once the policy support tool has been completed, it'll be made available to city authorities and policymakers so that they can establish what is going to be the likely effect of a particular scenario, say for example congestion, based on changes that are likely to take place as automation becomes a reality. Now, I mentioned the use cases and sub-use cases in the previous slide, and much of the work that we've done in the project has involved looking at these different use cases and the predicted changes that are likely to occur as a result of what happens when the theory becomes a actualization. For example, using traffic micro-simulation and mesoscopic simulation, we've been assessing likely changes to parameters such as journey or travel time, congestion, or traffic conflicts, emissions, etc., and the amount of travel people are likely to be involved in. And we've also developed a system dynamics approach for looking at effects on public health, commuting distance, parking demand, etc. We've used a driving simulator study to look at changes in driving behaviour, and we're using operations research to look at metrics such as fleet size, total kilometres driven, vehicle operating costs, and in some cases we adopted a Delphi model on top of all that. In other words, surveys and questionnaires for scenarios where we can't approach the analysis using the methods that I previously listed. So I think you can see that a good range of approaches have been used to good effect, I think. So these are the sub-use cases that I mentioned in the previous slide, and these are essentially the scenarios which underpin the project in its entirety. And as you can see, the sub-use cases or the use cases then determine what the sub-use cases are going to be. For example, we might start off with the premise that automation will have a substantial impact on urban mobility. But within the concept of urban mobility, we want to dig a little bit deeper than that to understand in what way urban mobility might be affected. And this is where the sub-use cases become so important, since we know that urban mobility is going to involve changes in the adoption of things like urban shuttles, either at a single point-to-point level or at an on-demand basis. And that's why each use case needs to be subdivided into each of its constituent parts, so we can see how one impacts on the other. So this is the first example of a sub-use case to discuss today. This is a traffic simulation, micro-simulation approach on the Manchester Road network in the UK. We looked at the likely impact on delays and crashes, and we've made some assumptions about what we're calling market penetration rate of autonomous vehicles as they progress from where we are now to 100%. So we've gone from 100% human-driven cars all the way up to assuming that we'll reach at some point in time 100% autonomous cars. What is interesting is there's a sharp reduction in delay time until we get to the point of only about 40% of the vehicles are human-driven, and then delays start to increase before falling off again. And you can see some irregularities are in the data here, which appear to be a function of the transition from low to moderate to high penetration, market penetration rate of connected and autonomous vehicles tested on the various networks in the micro-simulations. And in turn, this could perhaps be attributed to assumptions used in the model to model the first and second generation connected and autonomous vehicles. In this regard, we've had some mixed opinions about from a variety of experts about what's likely to happen in this regard. Some experts have indicated that there will be a progressive reduction in delay time with increasing market penetration rate of autonomous vehicles, while others predict small or no significant reductions in the long term. What you can see here is that emissions also decrease quite substantially. So we've got reductions in CO2, nitrous oxide and particulate matter. And of course, this is all because the all of the connected and autonomous vehicles we're considering within LEVITATE are electric vehicles. To examine the effects of dedicated lanes within cities, we undertook some microsimulation, again using the Manchester road network in the Pendleton area, for those of you who know Manchester, using AIM-SUM simulation software. We took a couple of the major roads in Manchester and assumed that they were dedicated lanes for autonomous vehicles. We can make a maximum travel time saving at a moderate market penetration rate, by which we're saying 60 human driver, 40 first generation autonomous vehicle on an A road with the left lane scenario. In other words, the left lane is the dedicated lane with other lanes provided for non-autonomous vehicles. And then on top of that, a Delphi study that we conducted also indicated that the left lane placement is most affected in terms of travel times. And if you do that, then you get a travel time reduction of around about 10% in the best case scenario. We also noted safety impacts through reduced crashes and conflicts obtained through surrogate safety assessment. In fact, a significant reduction in collisions was reported by the implementation with this particular sub-use case, and also an important decrease in emissions, particularly CO2, suggesting a very positive environmental impact with this particular sub-use case. In terms of parking management, two sub-use cases were explored: replacing on-street parking and parking pricing. Regarding replacing on-street parking with driving lane, cycle lane and public spaces, the interventions of removing half of the on-street parking spaces and replacing them with pick-up, drop-off spaces, etc. Indicates a better performance. For parking pricing, the results were a bit mixed. As you can probably see here, it's going to take some time following the introduction of autonomous vehicles until consistent reductions in travel time are going to be realised, because it varies in terms of the context of the market penetration rate of the first and second generation vehicles, and probably also the road network. So there's definitely a little bit more work to be done here to understand how policy changes regarding parking charges will impact on travel and travel time. For automated shuttles, this is a sub-use case we looked at here. The results indicated that the introduction of connected and autonomous vehicles in urban transport will definitely reduce travel time, almost regardless of market penetration rate, when comparing the situation in the context of a typical 5-kilometre urban trip. So some very positive benefits can be expected through the introduction of such urban shuttle services. For automated ride sharing, travellers' willingness or unwillingness for that matter to share rides has a direct impact on travel time. So the higher willingness to share will obviously bring benefits in terms of lower travel time. Lower willingness to ride share, which might also be a factor, has no benefit on travel time for anyone. In fact, it makes travel times, if anything, longer. So encouraging ride sharing would appear to be the most important dimension of urban or automated mobility. In this analysis, we looked at the effects of vehicle automation on freight transport, and as you can see here, we predict a small effect on the overall congestion in the urban environment, since the automated delivery vehicle share of the traffic volume is likely to be minimal compared with other vehicles. Nevertheless, quite an obvious advantage of automated freight transport is its ability to utilise off-peak hours and nighttime driving, etc. And so you've got benefits that can be realised there. We also estimate that fleet costs are also likely to diminish with the introduction of automated delivery vehicles, which is a benefit for most, if not all, commercial users of automated delivery services. We also use a system dynamics method to estimate the wider impacts of the LEVITATE project. And I guess the main thing to say here is that with increasing market penetration rate, all of the indicators in terms of active travel and modal split decrease with increasing market penetration rate of autonomous vehicles in the transport system compared to the baseline condition. This trend was also found to be common under implementation of all sub-use cases, but the relative impact compared to the baseline was found to be quite diverse, and the effects maybe not so clear. So we've got further work to do here, an additional analysis in order to consider these metrics in more detail. So overall, I think we're of the opinion that once connected and autonomous vehicles are truly level 5, if that point can ever really be realised, then there are going to be benefits across most, if not all, of the impact dimensions. However, during the transition phase, there appears to be an irregular balance of benefits and disbenefits based on the market penetration rate of connected and autonomous vehicles. But this can be mitigated through various suitable policy interventions. Certainly that we feel first generation connected and autonomous vehicles are likely to be less capable than human drivers, and this appears to affect several traffic safety and efficiency indicators. So further research might be indicated to examine these in more detail. Overall, the manner in which CCAM services are implemented is likely to change the nature and effect of the impacts. But what is clear is that some impacts may actually be greatest when we have less than 100% market penetration rate. Finally, a relatively urgent requirement is the need for better knowledge of how connected and autonomous vehicles will behave in relatively complex urban environments where you've got a mixture of road users, many of them unpredictable. And as yet, I think that's still a bit of an undiscovered piece of research that needs to be done sometime in the future. So thank you very much for listening.